Greetings to students of the internet, and today I'd like to do a small recap of what we did on our previous session. It's like a revision exercise, and then from the revision now we proceed and do charge controller sizing and solar panel sizing. So by the end of this session, I think I have explained well enough for you to be able to size an inverter and the battery bank capacity, and then we will do the the pulse with modulator charge controller sizing, and then the MPPT charge controller sizing. So I will display a small exercise that I had given to some of my students, which will guide. Now, this is a different exercise from the first one, but the working principle is still the same. It's basically a question to now guide what we are doing. So the question reads, as you can see on the screen. I will put the question on the screen. Good morning. My name is Mr. Edwin and I live in Kakamega County. I'm interested in installing a small solar power system for my home as I wait for KPLC to connect me to the grid. My household mainly uses the following basic electrical appliances. So the appliances are the ones listed here, appliance number 1 to appliance number 9. And question number 1 says, determine the total daily energy consumption, watt hour per day, which is this, the watt hour per day. And then question number 2, suggest a suitable inverter rating that can safely run the listed appliances simultaneously. Keyword is simultaneously. Now, this from our previous session, we learned how to generate this value, and I'll just go through it very fast. But question number 3 says, recommend a suitable battery capacity, AH and V, that can provide 1 full day of backup. 1 full day. So for the V, we will work with the 12-volt system because it's the basic system that level 4 students are supposed to learn. And it's also the most common system actually in the market. But later on, after we finish this, we can redo the same exercise but use a 24-volt system and then 48-volt system and see how different it will affect our overall size and the capacities of the different components. And also we shall also now analyze the financial aspect of changing the system voltage from 12 to 24 and then 24 to 48. And then present your results neatly in a table or report format, explaining all assumptions and system losses. So for a start, from that table, we will generate the rest of the values because the table is giving you the quantity, the rating. So it has listed the appliances. It has given you the quantity of the appliances, the rating of each appliance, and then the estimated hours of use or the daily operating time. So you as a technician is supposed to fill the total consumption in watts, and this is what will give you the inverter capacity to allow you to run all these loads simultaneously. And then the energy demand in a day in watt hours, this is what will guide you on determining the battery bank capacity. So to begin with, what you do from the table, you just fill in the values. I would like you to fill in the values, and also if possible, you can add a few appliances here. Now go for the very basic appliances, and you can share the appliances you've added so that we can revise together. Use my WhatsApp number. It will be appearing on the screen somewhere here. You can use that, share the work that you've done. Let's go through it together. Step 1, the inverter sizing. So based on this value, we are supposed to now, question number 4 says, present your results neatly in a table report format, explaining all assumptions and system losses. So from this value, we are supposed to generate our inverter sizing, and we explain our assumptions and system losses. So the inverter sizing or the inverter rating, the first value we use is the base value, which is 455 watts. The 455 watts, how do we generate it? You take the consumption value of each appliance, you multiply by the number of appliances in each, the number of appliances in the installation, you get the total. So for each appliance, for example, those that are more than one, the LED lamps, one LED lamp will consume 10 watts. And since there are 6, you multiply by 6 to get 60 watts, and then you add all these values. So if, for example, phone charger, we have one charger is consuming 5 watts, but we have 4 of them. So it will be 5 times 4, you get 20, and then you add to get 455. So this is the base value of the inverter. The first thing we do, we introduce a safety margin to the base value, and that is so our safety margin, we are operating at 50% safety margin, and we explained why we need to add a safety margin from the previous lecture or the previous session. So if you click on the link somewhere up here, or you just go to the same playlist session, the lecture titled session 2, it will explain why we need to add a safety margin. So our safety margin is 50% of this value, which is equivalent to 227.5 watts. So the base value plus the safety margin, we get 682.5 watts. Now, after we've introduced the safety margin, we factor in inverter efficiency. So since this is the amount, the total consumption in watts, so this is what the inverter is supposed to allow to be consumed in watts. The inverter acts like a gate. We explained that in our first lecture. So since it's supposed to allow 682.5 watts on the output, on the input side, because there are some system losses occurring, assuming our inverter is operating at 95% efficiency, it will pick a higher figure or a higher value and drop some for it to deliver 682.5 watts. And that higher value, we calculate it this way. We assume if 682.5 watts is equals to 95%, what is our 100%? So basic cross multiplication, basic math, so that is 100% times 682.5 divided by 95%. We are getting 718.4210 watts. Now, the Kenyan market, or the most common inverter components you'll never get an accurate value based on calculation. You might get 1,000 watts here, which is in a very lucky situation, but in most cases, the figure you'll get here won't be equivalent to the market available components. So for example, if I go to the market today, and for example, if I go to Alltop's Electronics, and I ask them to give me a 718.42 watts inverter, they don't have that. They'll have an inverter that is smaller than this or bigger than this, because there's no exact, this is a calculated value, but the manufacturers will normally give you specific figures. Like I've seen Alltop's Electronics have got a 300 watts, 600 watts, 1 kilowatt, 1.2, 1.5, I think, then as you go. So for electrical installations, to be safe, we go a value higher. So now the next value here is 1,000 watts. This is the nearest highest value in inverter capacities. So we'll operate with the 1,000 watt inverter. At this point, if you size your system to this point, these components can be supplied with a 1,000 watt inverter, all of them simultaneously, safely. If you do that, you are okay as a technician. So since this is a revision, I'll just go through it fast enough. Lecture session 2 has got all this information in detail. Battery sizing. So with battery sizing, this is the value we use to calculate the size of our battery. And how do we go about it? So the daily energy demand, the base value, this is the base value, is equivalent to 1,950 watt hours. 1,950 watt hours. Now, we have said that we are operating with a 95% efficient inverter, and this is like best of the best in terms of inverter quality. So if we are operating with a 95% efficient inverter, it means the inverter will be picking a certain amount of power for it to deliver 1,950 watt hours. So because it will be losing some there will be some losses occurring because of conversion and resistance and other things. And we have explained all that in our previous lecture. So if the inverter is operating at 95% efficiency, and this is our daily energy demand, it means the demand will be higher than this on the input side of the inverter for it to deliver 1950 watt hours. So same calculation, if our inverter is delivering 1950 at the output side, and that is 95% efficient, what is the 100%? Basic calculation, you will get 2052.631 watt hours. So that is like 1950 times times 100 divided by 95. You get 2052.6315 watt hours. So this is the first assumption you have to indicate based on the question. Make sure that both, if you're doing this for academic purposes, make sure the examiner knows this is your first assumption, that because the inverter is operating at 95% efficiency, it will be picking up bigger value but delivering 1950 watt hours, and our bigger value is 2052.6315 watt hours. So because we have said that we will be using our basic system voltage, that is 12 volts for level 4 students, to determine the energy demand in AH, because AH is the language that most people understand when it comes to battery sizing, not the watt hours. Although I've seen with the emergence of more manufacturers and more players into the solar components, I've seen that gadgets are coming that have got all this information indicated. So it could be a battery that is rated at 300 Ah or 400 Ah, but the manufacturer has gone ahead and displayed the watt hours and everything. So it's okay if you can work with this and understand between and communicate well between you and the salesman of the person you are sourcing it from, that is okay, but you have to convert this figure into AH for you to get the exact battery capacity. So we divide by 12, we are getting 171 AH. Now, another important assumption we are going to make is that because we are in Kenya and almost near the equator, Kakamega, we are assuming that this client will be receiving enough sunlight almost throughout the year, nothing less than 5 hours a day throughout the year. So that means we shall limit our days of autonomy to 1 day, that is equivalent to 24 hours. But even then, I will still advise you, or I'll still encourage you, if you are really looking into sizing a system based on this client's very specific demands, you can also calculate this to as little as 12 hours. That is equivalent to 6 p.m. to 6 a.m. So for now, let's calculate with 1 day, 24 hours, which is the most ideal day value when calculating the days of autonomy. And also, we have talked about DOD in our previous session, but I'll also link something here for you to go and look at. The batteries we are using, these are lithium ion batteries. They can allow you to discharge them up to 20%. That means you can take 80% of the charge capacity out of the battery and it will still operate to its full life cycle or lifespan. If we do this same calculation, but instead of lithium ion batteries, we use lead or gel batteries, this 80% value will change. And for lead, we have said we will be using 50%, and for gel, we'll be using 60%. So this is the maximum amount of charge that you can take out of the different batteries. So this is lead, this is gel, this is lithium ion. So ensure you indicate why you are using your, why you, how you approach these percentages. So if you just indicate 80% and don't explain that you are using 80% because you intend to use a lithium ion battery, you might confuse either your invigilator, your examiner or your client. So indicate, if you change this value, indicate and say I'm using 60% because I'm going for gel batteries, or the client can afford gel batteries, because the different battery chemistries also affect the financial decision that will be made overall. So the battery capacity, you take your 171 Ah times 1. So this one is the days of autonomy. So if you want to this system to run probably 3 extra days without needing to be charged, without, so that means you can go between the last time you charge it and the next time you charge it, you want to allow 3 days in between, you use 3 here instead of 1. If you want to size your system to just run probably overnight, I'd still encourage you to use 1, but you can use 0.5, meaning to assume that this system will only be working for 12 hours overnight. But for the right practice as a technician, if for the very minimum days of autonomy, I'll encourage you to use 1, never go below 1. As good practice. So we'll use 171 times 1 divided by 80%, and this 80% we've said is the depth of discharge. If we change this value, or we intend to use a different battery chemistry, let's say lead or gel, we'll use here 50 or 60 depending now on the battery that we will employ. So when you do this math, you get 213.75 H. Now, at this point again, ensure that you inform your examiner or your client of this assumption of the safety margin. And this means if at any given moment the client might have visitors, or he might add an extra component to this system, this safety margin is there to accommodate for that, because you are sizing this system in the past, but it is going to be used in the future. And the future does not, unless the client tells you to add these components here, all of them, at the time of sizing, you might not be able to account for extra items. So introduce this safety margin just in case something extra small is added to that appliance list. And this something extra small could be very basic, could be something like, let's say for example, when sizing this system, we said the children were in school, and then when they come back, the client adds an extra computer here, or buys an extra lamp, probably for security. A slight variation here will increase this value and this value. So that's why we introduce our margins, and that's why we have to explain them to our both the examiner and the client. So with our 50% safety margin, we add the battery capacity plus the safety margin, and our battery capacity is 213.75. The 50% safety margin is 50% of 213.75. That will be 213.75 plus 106.875. You get 320.625 AH. So at this point, if you size your system and your battery and you get to this value, this is the most ideal value you can operate with, or you can safely tell your client to, or you can use to approach the salesman to now supply you with the batteries. So because in most cases you won't find a 320.625 Ah battery. If you find it, well and good, but if you don't find it, you can now do this basic math. If we use a 12 volt 100 Ah battery, how many batteries will we need? So we'll take 320.625 divided by 100, we get 3.20625 batteries. Now in this case, we can go with 3 batteries, and we have to make this assumption well known. We can use 3 batteries because in any case, we've already factored in our DOD correctly. our days of autonomy correctly and our safety margin. So we can ignore the 0.2 for this particular configuration. And also make sure that assumption is known, well communicated. So if we go with a 12-volt system, 150 Ah batteries, we take the same value, 320.625 divided by 150, we get 2.1375 batteries. Also in this case, we can go with we can go with two batteries and ignore the 1.375. And in our assumption, make sure we include the fact that we factored in the DOD, the days of autonomy, the depth of discharge, and we've also factored in our safety margin, so we can use two batteries. So if we go with 12 volts 200 Ah system and we divide same value 320.625 divided by 200, we get 1.603125. Now, because we've already crossed the mid value 1.6, the nearest, the most reasonable assumption here will be to use two batteries, because if we factor in the 0.6 capacity of this, it will take away almost 50% of what we had factored in as safety margin. So for this case, I'll just advise you to go higher and use two batteries. Now, this was just a basic revision, but I intended to use these same values now to develop our charge controller, to determine the capacity of our charge controller and the solar panels. So I'll allow you probably you could pause at this point, do some basic exercises up to this stage, introduce probably 2-3 other loads here or appliances. You could change the daily operating time just to, because the minute you change some of these values, they could either add or reduce the daily energy demand. So just do some few exercises. You can screenshot or send as PDF, whichever way you find comfortable. Send them to my WhatsApp number. It will be appearing somewhere here on the screen. We will look at it. We can do more practice together. So this is for level 4 students. This is the the very basic way of calculating your inverter and battery sizing. Now, I'll take a few minutes. For you, it will be a few seconds, but for me, I'll take a few minutes and write down now how to size our charge controller. Let's proceed with our charge controller. I'll put here some basic information of the panel that we intend to use for this system, but let's proceed. So keep these values somewhere. You will write this value. So the inverter efficiency, 95, write it somewhere. The battery capacity, we've said, is 320.625 Ah. Also write it somewhere. So in this case, we've decided that based on the client's financial ability, you can pick either of the three systems, or even if you get a 400 Ah battery, if you use a 12 volt 400 Ah battery, you can just go for one. If you go to the market and get a 400 Ah battery. All right, I hope this is now well understood. Let me proceed with now charge controller sizing hours. Battery efficiency. So battery efficiency is not the same as depth of discharge. Depth of discharge is the total amount of charge you can extract out of the battery. Battery efficiency is equivalent to how easily can it allow power to get in and out. So if they're sending in 100 watt hours, how much will it allow? How much of the 100 watt hours will it allow to come in, and how much of the 100 watt hours will it allow to get out? So the required charge energy from the panels is equivalent to the inverter input power times the battery efficiency. So when you do this calculation, the inverter input power, that is 2053 watts, divided by the battery efficiency 90, you get 2281 watt hours. So this is the required charge energy per day, 2281. So that is the base required energy per day. But we will oversize our panel system so that they can, in case it's in a gloomy day, because in East Africa we have at least enough seasons where we get maximum amount of sunlight. But just in case there's a day where we don't get the 6 hours that we assume is the maximum amount of sun hours, we oversize our system so that the little extra can push enough charge energy into the battery. So a safety margin of 50%. Now this 50% is the 50% of the required charge energy. You get 1140.5 watt hours. So the overall solar output that will be needed for this system to charge effectively in a 6-hour period will be equivalent to 2281 watt hours plus the safety margin. You get 3421.5 watt hours. So we make the first assumption. If we are using a PWM controller, and we will explain the difference between a PWM and an MPPT controller immediately after this lecture. The next lecture is actually the difference between a PWM controller and an MPPT controller, and why which one is effective where. So if we are using assumption 1, if we are using a PWM controller, and we have said the effective sun hours is 6 hours on average, our solar output, each panel will be required sorry, not each panel. The solar output will be 3421.5 watt hours. This is the solar output divided by the 6 hours. So for every hour, we require panels to output 570.25 watts for every hour. Now, because we will not get a 570 watt, you are normally lucky when you do this calculation and just land on a figure that is equivalent to a market ready component. But since we will not get a 570.25 watt panel, we can either use a smaller panel or a bigger panel, and now work with the configuration either in series or parallel to ensure that we get this 570.25 watts. So in this case, we have bigger panels. Luckily, we can use a 625 watt panel. So in this case, we'll just need one panel. So for this system, if we use a PWM controller with one panel and effective sun hours, we assume that we will get 6 hours of sunlight, we can use one panel and charge this system every single day effectively. If we use a smaller panel, let's say a 325 watt panel, it's smaller than this figure. So this is an assumption. Now, these assumptions are also approached depending on the financial abilities. Most of them are normally financial decisions. So if a financial decision allows you to just go for one 625 watt panel, that is okay. If the financial decision will not allow you to go for this 625, you go for a smaller one probably, or even two. You can, if the financial decision is, if the financial capability of the client is okay, they can go for this two. Or if we use a 325, for this case, use any value. Just pick any panels in the market. Now play around with these values. They will just help you understand the system even better and correctly. So if we use a 325 watt panel, we'll get two panels. So I'd like you to do an exercise, assuming we use a 350 watt, 425 watts, 515 watts, and what else, 615 watts. So these values are just generic. Just play around. Let me see how you make your decisions based now on this particular assumption. Now, assumption 2 is if we use an MPPT controller. An MPPT controller is a maximum power point tracking controller. It functions differently from a PWM controller, and we will explain that in the next immediate lecture after this. So for an MPPT controller, we also have to factor in the controller efficiency. In this case, we are assuming we are picking the best of the best controllers in the market. You can get a very good controller, for example, okay, if you get a very good controller, it will allow you to, whatever amount of power you're picking from the panels, 90% of it will be delivered to the batteries. So the solar output, we still are working with this figure. So if the solar output is expected to be 3421.5 and the controller efficiency is 90%, and so it means the solar panels should be generating more for the MPPT to peak, sieve, waste some, lose some during the conversion process or during the transfer process. So it will pick a bigger value that will be 3801.11 watt hours from the solar panels. Now you'll notice that this figure is bigger than when we're using a PWM controller, and we will explain why in the next lecture. We will maintain the effective sun hours, the standard 6 hours. So the solar output will be 3801 divided by the 6 hours, you get 633.518. Now, assuming we go for the same panel size, 625, we use a 625 watt panel, we will need one panel, and this is on the lower side. So you can get two 625 watt panels, two of them, but that will be on the extreme higher side because the difference here is very small. So because we factored in a lot of safety margins and everything, one panel will be okay on the lower side for this system. Now, if we go lower, let's say we use a 325 watt panel, this is the value we get, we will need two panels. So for this case also, use these values. Let me see how you play around and for 350 watt, 425 watt, 515 and 615 watt. Let me see how many panels you will go for or you will go with in such a case. Now, at this point, let me make it clear. This was the size and number of modules you'll need or panels you'll need on the roof. This is not the size of the PWM controller or the MPPT controller. So now after this, the next session now, I want to talk about how to size the PWM. Let me make it easy for some of the students, because in such a case, the level 4 student doing a standalone solar system, to this point, I think this is the highest point you will go in terms of component sizes. And if you're going with the modern day components, for example, you will combine this with the already existing components, for example, with a 20 amp charge controller on the higher side. And our inverter was 1 kilowatt inverter. If you go with a smart inverter or a more advanced inverter, the inverter has got an inbuilt charge controller that will do this for you. So you don't need to know how to size the charge controller. But for those who are interested in learning beyond this point, let me teach you how to size the PWM. For level 4 students, I think at this point you are free. You can size your system up to this point. The rest doesn't matter. You'll just go with standard readily available components, and I will list them independently for you. For the cables, for the panels you've seen, you can go with the 625 watt panel. For the cables, I'll encourage you, use 6 squared millimeter flexi or solar cables or DC cables. 6 squared millimeter double insulated solar cables, flexi or solar cables, whichever term you'll remember. Use 6 mm almost all across the system. For you, the 6 mm cable will work. Between the inverter and the batteries, you can go even higher. You can utilize 10 squared millimeter cables. If the client is okay, go even for 16 squared millimeter cables. The math behind cable sizing is a bit advanced for you at this stage, but when you do electrical installation and solar installation at level 6, we shall also redo this math. We will refer to this video, hopefully, if we get there with all of you, and we'll refer to this video and know now how to size our cables, our protective devices. Yes, our cables and our protective devices. For those who are interested in doing this beyond level 4 for the academic purpose, but not advancing to level 6, let's size our charge controllers with you. So the assignment that I'll be giving, assignment for my students. For those who are not my students, you can just practice independently. Do this using the different panel configurations, not configuration, the different module sizes in words. Let me see how you play around with these figures and see which one is more effective for your system. So I want you to tell me, if I use a PWM or an MPPT and I'm using a 615 watt panel, which one is more effective? I want to see how well you think beyond the math.